Okay, this video will cover chapter 6, section 1, 2, 3, three sections. All right, so this chapter is about the probability, right? What is the chance of something happening? So probability, whenever we mention the word probability, we should have something like this. Probability is a part of something over the whole thing, right? And at most, it can be 100%, which is 1, 100%, which is 1. Or at least it can be 0, so no chance of happening, which is just 0. So that's a probability of any event. So probability of any event in between of those two numbers. So whenever, right, we see the word of probability, we should know there's a number in between 0 and 1, in between 0 and 1. At least 0, at the most 1. There's some numbers in between 0 and 1. It cannot be negative. It cannot be more than 1. All right, so that's just a number sense. Okay, let's see section 1. Section 1, we need to get familiarized with some terms. So the terms here we have experiments, outcomes, sample spaces, and events. All right, so we're going to go over all of those. So an experiment is an activity or observation. Okay. Each possible result is called an outcome of the experiment. The set of all possible outcomes is called the sample space. Right. So all possible results, right? Because each result can be called an outcome. And when we put all outcomes, possible outcomes together as a set, right? As a set, so we call sample space. And then the word event. So event is a subset of sample space. So we see that the event E has occurred when with the outcome of experiment is an element of E. Okay, we will use example to understand what are those terms. So example 1, let's say rolling a die, right? Imagine I have a die, 6 sides. So basically it's a cube, right? And the 6 sides, each side has a number. Sometimes it's with a dot, sometimes with a number. Well, maybe 2 dots representing 2, maybe 3 dots representing 3. So 4 dots, 5 dots, 6 dots. So I have 6. So, okay, in this case, let's just write down 1, 2, 3. 1, 2, 3, maybe the bottom is a 4, the left-hand side is a 5, the back is a 6. So imagine you have a cube, each face has a number, right, from 1 up to 6. So the sample space is 1, 2, 3, 4, 5, 6, all possible outcomes, right? Imagine you toss a die. Imagine you toss this die, right? You toss this die once. When it's landed on the number, so let's say this case, right? In this case, just suppose I toss this die and landed like this. So the face value is 1. The face value is 1. So the outcome is 1. But the possible outcomes could be 1, could be 2, could be 3, 4, 5, 6. So 6 possible outcomes. So that makes a sample space. And the cardinal number of this sample space is a 6, right? 6 elements. Right? So all possible outcomes makes a sample space. And we call this experiment. So when we toss this die once, that's one experiment, toss twice, right? So on and so forth. So a possible event could be just one, right? I'm looking for one. Maybe I toss this die 3 times. I'm looking for one. So the possible event is just one because my interest is one. So event you can think as interested possible outcomes. Let's say C. C, so one possible event is 2, 4, 6. Right? 2, 4, 6. So we toss this die. It could be 2. It could be 1, could be 2, could be 3, could be 4, could be 5, could be 6. But we're interested in finding out to get 2, to get 4, to get 6. So that's event. So event is something we are interested, right? So interested in. So in this case, also, we could see this, right? Could make the set as this. The event that the outcome is an even number, like total possible outcomes from 1 to 6, and the even numbers are the 2, 4, 6. So let's see this case, right? This one, we're going to roll a pair of dice, right? So 2 dice. So basically all, we're just rolling 1 die twice. So think about it. Well, usually for 2 dimension, but think about this event as 2 dimension. So we have a first die. So this is the first, right? The value of the first one could be 1, could be 2, could be 3, could be 4, could be 5, up to 6. So let me use red color maybe. Right, so this is the first die. Could be 1, 2, 3, 4, 5, 6. The second one, let me use blue. So this column, so the row records 1 die, 1 possible outcomes of first toss. Then the column represents another one. So 1, 2, 3, 4, 5. Let me make one more. Right. So I have 1, 2, 3, 4, 5, 6. So that's how this list is the same thing as this list. But if we make a table like this, right, the 2-dimension table like this, maybe we get 1, 1, which is this one, right? Which means the first toss is 1, second toss is 1. Or maybe you get 2, 1. The first toss is 2, second toss is 1. Maybe the first toss is 3, second toss is 1, so on and so forth. So here we made a list. So this is a sample space. It's a sample space when we toss 2 die. When we toss a die 2 times, or same thing. If you have 2 die, you roll the 2 die simultaneously. Or if you don't have 2 die, you have 1, you roll the die twice. All right. So the first number represents the result for the first one, or the possible outcome for the first toss, or for the first die, so on and so forth. And the second number represents the second toss or the second die, the face value. The face value. So when you toss a die, it will land it on a face value. So which is this one, whatever the value is here. So that's how we count the die. When we toss a die, we count the face value, the number on top. Right. So those are all possible outcomes or sample space. How many we have? You see, we have 1, 2, 3, 4, 5, 6. 6 in a row. Well, 1, 2, 3, 4, 5, 6. 6 in a column. So 6 times 6, the cardinal number is 36, right? So similarly, as we talked about earlier, if we want to complete a task, yeah, we have m ways. We have m ways for choice 1, right? We have for choice 2, we have n ways. So to complete the task, including those 2, we have m times n ways. So you see the similarity here. But for the first toast or the first die, we have 6 possible outcomes. For the second toast or the second die, we also have 6 possible outcomes. 6 times 6, so total the sample space or all possible outcomes are 36 of them. That's how you make a list. Okay, normally what do we care about? So when we toast this die, 2 die, or toast a die twice, we could think, okay, the sum of the 2 face values, right? You see the red color represents the first die, blue color represents the second die. If I toast 1 for the first, toast 1 for the second, 1 plus 1, so here I can write down 2. First one is 2, second one is 1, here adds up to be 3. Well, first one is 3, second one is 1, adds up to be 4, or 5, 6, 7. Or the first toast is 1, second toast is 2, 1 plus 2, 3. Right? So 4, 5, 6, 7, 8. So on and so forth. We just add up. So 5, 6, 7, 8, 9. Then 5, 6, 7, 8, 9, 10. First toast is 1, second toast is 6, 1 plus 6, 7. First toast is 2, second toast is 6, 2 plus 6, 8, 9, 10, oh, here, 7, 1, 2, 3, 4, 5, 6. Oh, I made 1, 2, 3, 4, 5, 6. Oh, I missed 6 here. 6, 7, 8, 9, 10, 11. 7, 8, 9, 10, 11, 12. 6 plus 6, 12, right? The first toast is 6, the second toast is 6. Or the first die is 6, second die is also 6. That adds up to be 12. Then we can ask a probability questions, right? We can ask a probability question like, what's the probability regarding probability? Right? We say, okay, the event, remember event is something we're interested, right? The event could be 7, right? So usually we use E represent the event. Then we can ask us, when I toast 2 die, what is the probability for me to get the sum to be 7? The sum to be 7, right? So the event is the sum, or right here, sum is a 7. Well, total I have 36 of them. So that's a whole thing, right? Whole thing is a sample space. Whole thing is a sample space. It's a cardinal number of the sample space. So the cardinal number of sample space is 36. So this is the sample space, right? When we talk about the summation, we just add those numbers. Just add those numbers. Okay, so we need to find out how many possible 7s, right? 7 as outcome, how frequent it happens. So here's 1, 2, 3, 4, 5, 6. Right, 6. So the probability when we toast 2 die, get the sum to be 6 to be 7 is 6 out of 36. If we want to simplify it, it's 1 out of 6. Right? Or maybe our event is 5. Right? So then we can ask, what is the probability for me to get the sum to be 5 when I toast a die twice, or when I toast 2 dies? Well, the sample space is still 36. So we need to count how many 5s. So let me use another color. Let me use green color. I have 5 here as a sum. 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 So 1, 2, 3, 4. I have 4 of them. So be very careful. You do not want to count this one, because this is the face value of the first die. And also you do not want to count this one. This is the face value of the second die. It's not the sum. The sum is those numbers in the middle. Those numbers in the middle, those are the sums, 36 of them. So that's 4 out of 36. We can simplify as 1 out of 9. Okay, this is a quick, very quick example for, why we want to do this. What do we care about when we toast a die twice or when we toast 2 die? So this example is saying the event, right? One possible event is the first die is 1, second die is 4. First one is 2, second one is 3. First one is 3, second one is 2. First one is 4, second one is 1. Right? So this event also can be described, the event that the sum of 2 numbers is 5. Right? Because when we add those 2 numbers, we do get 5. We have 4 of them. When we talk about probabilities, we talk about 4 out of the cardinal number of sample space. Okay, let's see example 3. Once every hour, a supermarket manager observes the number of people standing in the checkout line. The store has space for most 30 customers to wait in line. Illustrate the preceding definitions for this situation. Right? So we want to describe the preceding definitions for this situation. So let's see this solution. A is saying the possible outcomes are the numbers from 0 to 30, right? 0 means no customer on the line yet, in line yet. Or maybe 1 customer in the line, 2 customers in the line. So up to 30 customers waiting in line. So B is the sample space is from 0 up to 30. Right? Because we care about how many customers wait in line. That's an event we care about. Customers waiting in line. So possible values are 0, nobody waiting in line. 1 customer waiting in line. But the most 30 customers waiting in line. So that's a sample space. Sample space from 0 up to 30. So the cardinal number is 31. Right? Because from 1 to 30, there's 30 of them. Then plus 1 with 0, 31. So C, one possible event could be no customer waiting in line, could be 1, could be 2, could be 3, could be 4, could be 5. Right? Customers waiting in line. So this event also can be described the event that are at the most 5 people standing in the line. The most, less than or equal to 5. Right, those numbers in the sample space, which ones are less than or equal to 5? 0, 1, 2, 3, 4, and 5, because 5 equals to 5. Let's see this example. The Environmental Protection Agency ordered Middle State Edison Corporation to install scrubbers to remove the pollutants from its smokestacks. To monitor the effectiveness of the scrubbers, the corporation installed monitoring devices to record the levels of sulfur dioxide, particulate matter, and oxides of nitrogen in the smokestack emissions. Okay, consider the monitoring operation as an experiment. Describe the associated sample space. Well, each reading of the instruments consists of an ordered triple numbers X, Y, Z, because we have those different ones. So have scrubbers, and then we have we have this sulfur dioxide. We have this particulate matter. We have oxides of nitrogen. All right, so I have these three kinds of stuff to detect. So that's why we have X, Y, Z. Well, X equals the level of sulfur dioxide, and Y is the level of particulate matter. And Z represents the level of oxides of nitrogen. So the sample space thus consists of all possible triple values of X, Y, Z. And X, Y, Z can at least be 0, but cannot be negative. Right? All possible triples. So what is the sample space? We could write like this. Just X, Y, Z. And X greater than or equal to 0, Y greater than or equal to 0, Z greater than or equal to 0. That ends with this. Remember, this wiggly braces represent the sets. So the sample space is a set of X, Y, Z values, where X represents the sulfur, this, Y represents this, Z represents this value. And for X, Y, Z, it cannot be negative, which means greater than or equal to 0. As you can see, this we have right. It really depends. We have lots of possible values. So we see this four samples, right? 1, 2, 3, we have finite number many. So the first one we have 6. The sample space is 6. The sample space size, the size of sample space, or the cardinal number of sample space. Right? And the second one, the cardinal number of sample space is 36. And 3 is from 0 to 30, that's 31. So all finite number. But 4, X, Y, Z do not only defined as an interval from 0 up to infinity. So the infinite number set, infinite. So this set, the cardinal number of this sample space is infinity, right? So what is the size of this sample space? It's infinity. It's not a number. Because X, Y, Z, as long as they're greater than or equal to 0. So we have infinite many numbers in this set. Let's see 5. So question 5, suppose that an experiment consists of tossing a coin 3 times and observing the sequence of heads and tail. Let me use black color first. So coin usually has 2 sides. So we assume a coin never landed on the side. Either land on head with a person's head, or the tail, the back of it. The back of it usually is a building. Yeah. So head and tail. So if we toss this coin 3 times, so what are the possible sample space? Well, let's see. Let's just make a tree. So let's see first tossing, right? We may have head, we may have tail. Or second times. If the first one is head, the second one might be head or might be tail. If the first one is a tail, The second one may be head or maybe tail. So third one. If the first one and second one both head, and the third one may be head or maybe tail. If the first one is head, second one is tail, then the third one may be head, maybe tail. If the first one is tail, second one is head, the third one maybe head, maybe tail, right? Because each step, each level, you see you have two possibilities for each. Same thing. If we get tail for the first two, we may have head or tail, right? Two possibilities. So we always get two possibilities. So now we have this tree, right? You see this? This represents, so this tree branch represents the first one is head, the second one is head, the third one is head. So when we write in the sample space, we write this way. Just write H, H, H. So the H, H, H represents the first tossing is head, the second tossing is head, third tossing is also head. Or this one, or let me use different color. Or the first one is head, second one is head, but the third one is tail. We have this. So you see that's H, H, tail, which means the first tossing is the head, second tossing is the head, the third tossing is the tail. So on, so forth. How many you have? 1, 2, 3, 4, 5, 6, 7, 8. Right, so the cardinal number of this sample space is 8. Where does 8 come from? Remember last class we talked about the subsets, right? A set has 2 raised by its cardinal number. So in this case, what do we have? So before we tossing this head 3 times, each tossing, we could toss a head, we could toss a tail. How many elements we have? We have 2 elements, right? With 2 elements. So 1, 2, 3, 4, 5, 6, 7, 8. All right. So which is 2 raised by 3 because we tossed 3 times, right? Each time we have 2 possibilities. And then we first time 2, second time 2, third time 2, 2 times 2 times. So we get a 2 raised by 3, which is 8. All right, let's see B. B is asking determine the even E. Well, exactly 2 heads. Exactly 2 heads. Well, let's just draw from here. Exact 2 heads. So this one has 2 heads, this one has 2 heads, this one has 2 heads, and that's it. Right? So the even E equals to head, head, tail. Head, tail, head. Tail, head, head. So that's our even E. What is his cardinal number? 3. Right? If we ask what is the probability of even E, which means I toss this coin 3 times, what is the probability for me to get exactly 2 heads? Well, that's 2, that's 3 from here. Out of how many? 8. 3 out of 8, because the cardinal number of sample space is 8. Right? 3 out of 8. Okay, let's see this example. A political poll surveys a group of people to determine the income levels and political affiliations. People are classified as either low, middle, or upper level income, and as either Democrat, Republican, or independent. So 8, find the sample space corresponding to the poll, right? So the poll, so the people are classified as low, middle, upper. Okay, either low, middle, upper income, and as either Democrat, Republican, or independent. So the sample space. So let's make a sample space. So we actually will list the sample space. Well, it could be low, right? If you want, you can write low, or just use L to represent L, M, U to represent this. This is D, R, I to represent. Okay. Maybe low level income, right? Then could be that Democrat, or low level income could be Republican. Low level income could be independent. Or maybe middle income, right? Middle income could be Democrat, middle income could be Republican, or middle income could be independent. Or upper, right? Upper level income. Upper level income may be a Democrat, upper income with Republican, upper income with independent. So I have listed them all. So 3, what does this, 9, what does this 9 come from? You see we have 3, right? For the first one, for the income level, we have 3 for the political position. So 3 times 3 should be 9. And indeed, we made the list of sample space, it is 9. So B, determine the even one independent. Well, let's see. So E1 equals to, right, independent. It could be low income independent, could be middle income independent, or could be upper income independent. So I have 3 of them. B, E2, low income and not independent. So E2, low income, not independent. So it means, so this is low income independent. Well, low income, not independent is anything else except E1. So basically this is E1 complement. E1 complement, right? In the sample space, not in E1. So just the rest. So low income, Democrat, low income, Republican, or middle income, Democrat, or middle income, Republican, or upper income, Democrat, or upper income, Republican, or that's it. Like how many? 6 of them. So as you can see, even 1 and even 2 here are complementary. So which means E1 equals E2 complement, or E2 is E1 complement. Okay, lastly, D, determine even E3, neither upper income nor independent. So basically, E3 equals to, is a complement of sample space, right? Except neither upper income independent. Right? It's a complement of this, right? Upper income, upper income, and independent. So how many we have? Well, sample space has 9 elements. It should be 8 minus 1. It should still be 8, right? Could be LD, low income Democrat, low income Republican, low income independent, middle income Democrat, middle income Republican, middle income independent, or upper income Democrat, upper income Republican, just not upper income independent. So the cardinal number here is 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Because just 1 is not in the set. But you could list like this, all right? But usually you could list with open parentheses, first one, then comma, second one, close parentheses. Or just make a list like this, like what I did, all right? hold on a second. Why E3 only has, hold on a second. I have different answers than those, than the textbook. Right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, sample space we have the same. And the E1, 3 we have the same. So E2, let's see the question. Sometimes the wording is confusing. Let's see. So C is asking even 2, the income level is low and the political affiliation may be either Democrat or Republican in this case. Let's see. So C, let's see. Determine the even 2, low income and not independent. Oh, okay. Low income and not independent. Well, low income, not independent has 2, right? Because low income I, well, so which means not independent, which means either Democrat or Republican. Okay, I think I see the question wrong. That's why it's only 2, right? Only low income Democrat or low income Republican. Let's see D. What is D? Determine the event E3, neither upper income nor independent. So neither one of this. So neither upper, so only have lower, middle, nor independent. So we only could have Democrat, Republican. All right, it's the wording. But remember, so in this case, E are events, E1, E2, E3, so on and so forth are events. Well, with the events, and we represent with the sets, so we can take a union, we can take intersection, we can take a complement. So this is saying, let's see, we have sample space, contains 1, 2, 3, 4, 5, 6. And let's see, even E is 3, 4, 5, 6. And F is given as 1, 4, 6. Then we can talk about the union. E union F, which means the elements in E contains all elements in E and all elements in F. So which we have 1, we have 3, we have 4, we have 5, we have 6. We just don't have 2 in it. And the intersection, right? This intersection. Intersection means the elements in E and in F. So elements in both. We see it's 4 and 6. Right? 4 and 6 in both. So that's the intersection section. Well, complement means the elements not in E, right? E complement means the elements not in E, but in the sample space. So we see that's 1, 2. Well, also we can talk about F complement. The elements in S, not in F. We see 2, 3, 5. Right? 2, 3, 5. Also, we could visualize using Venn diagram, right? So you have 2 sets. We have E, we have F. E and F have some intersections. And E union F. E union F, we could draw. Let me use red color. So that all the elements with this within the red color. That's it. That's a union. E union F. Or intersection, right? This picture shows intersection. So those elements in the intersection are in E, in the circle E, and in the circle F. So the common elements. complement. We know inside this circle represents element E. So outside this circle, the E complement. Let's see this example. Consider the pollution monitoring described in example 4. Let E, F, and G be the events as such. E represents the event level of sulfur dioxide greater than or equal to 100. And F represents the level of particulate matter less than or equal to 50. G represents the level of oxidize of nutrition less than or equal to 30. So describe the following. Well, E intersect with F, right? Remember, intersection is in both, right? So E represents greater than or equal to 100. And F represents less than or equal to 50. Well, let's do this. Let's draw the line. So let's see 0 is here, right? So this is 50. This is 100. So E represents greater than or equal to 100, greater than or equal to 100 from this. So this is set E. And F represents less than or equal to 50, less than or equal to 50 here to this end. So this is the set of F. So what do we do? What do we do? So we do E intersect with F. We could use this, but better use this notation, right? We set the set notation. We want to use wiggly. We want to use a wiggly braces. We see level of sulfur dioxide greater than or equal to 100, and keyword, and because it's an intersection, and the level of particulate matter is less than or equal to 50. Okay, what's the E complement? Right, E complement, because E is the level of sulfur dioxide greater than or equal to 100. So E complement has to be less than 100. So E union G, right, again, let's stay with the set notation. The level of sulfur dioxide greater than or equal to 100 because the union now is war. It's war level of oxidize of nutrition less than or equal to 30. Union, remember, is or. Union is a bigger set. Intersection normally is a smaller set. If we do the intersection of E complement with F with G, so E complement is level of sulfur dioxide less than 100. Because it's the intersection, so we use the word and. And the level of particulate matter is less than or equal to 50. And intersection, level of oxidized nutrition less than or equal to 30. We end with wiggle brackets. Okay, so one property is talking about two events are mutually exclusive. Mutually exclusive, which means we have two sets. You do not, I don't have your element, you don't have my element. So the Venn diagram looks like this. We have E here, we have F here. Well, let's use an example. Or maybe we'll have an example later. So the two events does not have intersection. It's called mutually exclusive. Yeah, let's see this example. So S, the sample space, has A, B, C, D, E, F. Right. And the E is a subset containing the A, B, C. F is a subset containing the E, F, G. And the G is a subset containing the C, F, D. So are E and F mutually exclusive, which means E and F, which means E intersect F is empty set. Right? You either use a double wiggly parentheses or just use this. Okay, both notations means empty set. Okay, E has A, B, C. F has E, F, G. Yes, indeed. E intersect F is empty set. They don't have a common element. So they are mutually exclusive. What about F and G? Well, F is E, F, G, and G is C, D, F. So no, right? The first one is yes. E intersect F is empty set. Well, second one is no. Why? Because F intersect G doesn't have a common element, F. Because F is in capital letter F set, also in set G. So F and G are not mutually exclusive. Mutually exclusive means the two events has no common element. The intersection is empty set. Okay, that's section 1. Let's go to section 2. So now we want to assign events probabilities. So let's see some logical probability, right? Probability of a coin tossing showing heads. Probability rolling a 7 when a pair of dice. The sum, rolling sum to be 7, right? Probability of winning a Powerball lottery. So this is talking about empirical probability, which means by experiment, right? By experiment. So maybe, so probability has these 3 kinds of probability. Well, some people call logical, and a lot of people call theoretical. Theoretical probability. What does it mean? That means if I toss a coin, I have a head here, I have tail there, right? If I toss this coin, let's say 3 times, remember made a list. We have 2 times 2 times 2, we have 8 possible outcomes in the sample space. Right? Remember that we have edge, 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 head, head, head. We have head, head, tail, so on and so forth, and total 8 of them. Right? So this is a theoretical. This is a theoretical. So if you and me, you have a coin, I have a coin, you toss, I toss, each of us either toss 3 coins or toss a coin 3 times, we may not have this different result. We may not have the same results as this, right? So we could cut. So this is saying, remember we did the probability of getting 2 heads. Getting 2 heads. We could have HHT or HTH or THH. Right. What else could we could have? We could have a head, head, a tail. We could have a tail, head, head. We could have head, tail, head, right? So we could have 3. We could have 3. The probability would be 3 out of 8. But if you do or I do, different people do that, we may not get this theoretical probability. So we get something called empirical probability. Okay, empirical probability. If you want, you can get a coin in a toss to make a toss, right? To see what is the probability you get in 2 heads, right? When you toss the coin 3 times, right? So that's called empirical probability. So by experiment. And then another one is called judgmental probability, which is means by experience, right? By educated guess. It's very subjective. It depends on your experience, depends on your judgment. So we have three kinds of probability, right? So then, however, when we do calculations, we follow, except we do a survey or something. Usually, when we do the calculations, pure calculation, we follow theoretical probability. Theoretical probability. Why? Because, so the law of large numbers is a theorem. The law of large numbers unifies these three probabilities. The law of large numbers is saying, your empirical probability is different from theoretical probability. Your judgmental probability is difficult from theoretical probability. It's because you do not experiment enough times. You do not have enough experience. You do not conduct the experiment enough times. If you keep tossing, if you tossing the coin 1 million times, 10 million times, gazillion times, and the number will go to theoretical probability. So that's why when we calculate, we only follow theoretical probability. So this textbook is called a logical probability. All right. But if you conduct a survey, you want to study something, you conduct a survey, most of the time you use empirical probability because you want to conduct experiments. You want to get empirical probability, all right? But for calculation-wise, we follow theoretical probability or logical probability in this textbook. So let's see example 1. Forecasting rain. Classify the following probability as logical, empirical, or judgmental. Probability it will rain tomorrow is about 30%. You don't have to conduct experiment, right? You don't need to calculate. What do? You just do it by your judgment. You just go by your, this could be empirical or could be judgmental, right? It could go by your experience. So this is saying empirical. So weather probabilities are widely misunderstood. Some people think that the statement means that it will rain 30% of this area. Others think that it will rain 30% of the time. Actually, with what the weather person means is that, this is from a weather person. Forecasting. Yeah. Forecasting rain. Based on past observations when weather conditions are similar to today's weather condition, 30% of the time it rained the next day. All right, so this is by empirical, right? Because it's forecasting, right? It could be judgmental too, right? Could be judgmental. Okay, so probability has, so as I mentioned earlier, probability of any events has to be, probability of any events is a number, is between 0 and 1, right? 3 out of 8, 5 out of 36, right? It's a fraction. So fundamental probability is saying if you have n events, right, you add up the probability of all events, it has to add up to be 1. Has to add up to be 1. So let's see what does this mean. Let's say I toss a coin, head and tail, right? So what is the probability for me to get a head? Half chance, right? 50% either way. What's the probability for me to get a tail? Right? Imagine this is a fair coin, which means equally likely H and T happens. So probability of getting tail is also half chance, 50%. and add those two numbers, indeed it is 1. Okay. So that's what this means. Probability. So first probability is a number between 0 and 1. Second, probability of all events adds up to be 1. Probability distributions. Distributions is a word, right? So if I toss a coin, I have a head and tail. So probability for me to get a head is a half, half chance. Probability for me to get a tail is also half chance, 50%, but adds up to be 1. So distribution is like this. Probability of getting heads is 50%. Probability of getting tail is also 50%. For tossing a die, what is the probability for me to get a 1? 1 out of 6, right? Because sample space is 1, 2, 3, 4, 5, 6. This is my sample space. What is the probability for me to get a 1? Well, there's only one, so 1 out of 6. Well, what is the probability to get a 2? 1 out of 6. Probability of getting 3, 1 out of 6, because each one is unique. Probability of getting 4, 1 out of 6. Probability of getting 5, until probability of getting 6. So I have 6, we have 6 of 1 over 6, so adds up to be 1. So the probability of all events, right, adds up to be 1. So far we know probability is a number in between 0 and 1, and the probability of all events adds up to be 1. If it doesn't add up to be 1, it's not a probability distribution, right? If this is a probability distribution, because total, right, if I want to do here, I could write down total, it just equals 1. Same thing for this, right? This, if you total this, half plus half, that's 1. So this is called a probability distribution. If we do not add up to be 1, there won't be a probability distribution. Let's see this example. This example is saying a group of 95,505 college freshmen will ask this question. What is your intended major? Table 1 shows the results of this question. So intended major, so number of freshmen. The data was obtained from the American Freshman National Norms for 2019. Consider the experiment of selecting a student at random from the group surveyed and observing their answer. So intended majors, the number of freshmen. We don't see numbers here. Question A is asking, determine the probability distribution for this experiment. B, verify the probabilities satisfy fundamental probabilities 1 and 2. So for each eligible outcome, we use the data to compute its relative frequency. For example, of the 95,505 freshmen sampled, 9,264 intended to major in engineer. So the outcome engineering occurred in 9,264 over the part of something over the whole thing. That's about 9.7%. Therefore, we assign to the outcome engineering the probability 0.097. Similarly, we assign probability of other outcomes on the basis, right? It's a part of something over the whole thing. Right? So different intended measure with different measures. So probability is such, and these probabilities has to add up to be 1 in order to be probability distribution. So this is saying, use example 2, we cannot always rely on intuition to assign a value to a logical probability. Instead, we must use our knowledge sets and accounting to construct a theoretical or logical model of experiment log, along with the associated probabilities. This allows us to determine the probability for events rather than just single outcomes. So 4 heads. Oh, getting 0 heads, getting 1 heads, getting 2 heads, getting 3 heads, getting 4 heads. So the probability adds up to be 1, so it is a probability distribution. Okay, let's see this one. The addition and inclusion-exclusion principle. If you remember this one a little bit earlier, what do we see about that? We see E union F equals to E union F. No, not E union F. So E union F equals to E. Typically, we talk about the cardinal number of them. How many of them? That equals the numbers in E plus elements in F. Then subtract elements. Elements in F minus elements in E and in F, right? Because we counted both elements, we counted the intersections in E, you counted also intersection in F, you counted it twice. So we have to subtract once. Remember earlier we called this inclusion-exclusion principles. So this addition principle is saying, suppose that even E consists the finite number of outcomes, S1, S2, so on and so forth, up to Sn. That is, so the even E has this series of outcomes. So the probability equals to probability of E equals to probability of the first outcome plus probability of the second outcome plus probability of the outcome, so on and so forth. So let's use an example to illustrate this, right? Let's see this one. Remember our sample space. So roll a die, our sample space is 1, 2, 3, 4, 5, 6, right? Now we consider E as 1, 3, 5. So the odd numbers in the sample space. So what is the probability of E? Well, probability of E is 3, because we have cardinal number of E is 3, over the sample space. Well, sample space, the cardinal number of sample space is 6. So 3 out of 6, which is a half, right? This is one way to calculate. Or we could use the addition principle, seeing probability of E equals the probability of 1, which is 1 out of 6, plus probability of getting 3, 1 out of 6, plus probability of getting 5, that's 1 out of 6. Indeed, that's also 3 out of 6, which is a half. So they call this addition probability. Well, let's see this example. This example is saying, observe the sex and birth orders of each child in 2-child families and calculate the probabilities of 0, 1, and 2 males. So each family has 2 child, right? Let's see family 1. Family 1 has 2 child. What are the possibilities? It could be boy, boy, could be boy, girl, could be girl, boy, which means this means the first one is boy, second one is girl. This means the first one is girl, second one is boy. Or could be both girls, right? So similarly for family 2, I could have this kind of possibilities. So in this case, this set, because the order matters, does the order matter? I don't know, let's figure out. If the order doesn't matter, we only have to contain 1, right? So which means 1 is boy, 1 is girl. Doesn't really matter of who's the oldest, who's the youngest. So let's see, the sample space is FF, female, female. So this is a female, female, or girl, girl, female, male, male, female, male, male. Okay, does make the order does matter. So the older one is female, the younger one is male. The older one is male, younger one is female. So female and male denotes the birth sequence as the first child is male, female, second child is male. We assume equally likely to occur. So this is a theoretical probability. We always assume something equally likely. Every possible outcomes has an equally likely to occur. They have equal chance to happen. So we should assign probability 1/4 to each outcome, right? You see, because the sample space will have 4, so probability of getting female, female is 1 out of 4. Probability of getting female, male is 1 out of 4. Probability of getting male, female is 1 out of 4. Probability of getting male, male is 1 out of 4. Each one has a probability of 1 out of 4. But this one is just saying 1 male, right? The first one is 2 females, so no male. With 1 male, well, 1 female is the same, it's half, right? 2 males is 1/4. So probability distribution. So then we can make this probability distribution. A lot of times we use table to represent probability distribution. So this is a probability distribution. Right? We'll say, okay, female, female, that's 1/4. Male, female, or female, male, that's 1/2. Male, male, that's 1/4. Right? Let's see this one. Probability associated with college majors. So consider the college major survey of example 3. What is the probability that a student selected at random from a group surveyed intends to major in one of the 3 most popular fields outside the other and undecided notice? So the event is top 3 most popular fields is same as biological, life science, business, health, profession. So I have these 3, biological and life science, business and health professions. So the probability of the event is the probability of biological and life science, probability of business, probability of health and professions, Or earlier, remember that was a long table. We just add those three probabilities. This is just still talking about the addition principles. Let's see this one. Probability associated with a row of a pair of dice. Suppose that we roll a red die, a red one, and a green one, and observe the number on the side that face upward, so the face value. So calculate the probabilities of the elementary events. What are some elementary events? Right, we could have, remember, have a total of 36 of them. The sample space, the cardinal number of sample space is 36 of them, because each die has 1, 2, 3, 4, 5, 6 numbers, possible outcomes. Right? Green die, same thing, has 1 up to 6 numbers. So calculate the probability of the elementary events. Remember, I have 1, 1, 1, 2, da, 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 up to 6, 6. So 36 of them in total. B, calculate the probability that the two dice show the same number. Two dice show the same number. It could be what? So let's name this even E. Could be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And that's it, right? Because sample space is only from 1 to 6. How many of them? 6 of them. Right? But we want to calculate the probability. So what is the probability of E? Well, the sample space, how many we have? 36. And the E is our interested outcome or our desired outcome. What's the cardinal number? 6. So that's 6 out of 36, which is 1 out of 6. So that's the probability getting the two die number the same. Or we could just use the addition principle, right? What is the probability to get a 1 out of 1? That's 1 out of 36. Get a 2, 2, 1 out of 6. So we'll add all those 6 up. We'll also get a 1 out of 6. Let's see this example. A person buying a certain 10 scratch-off ticket will lose their $10. So that's cost of the tickets, $10. If they don't scratch any price amount, right, will break even if they scratch off $10, but may also scratch off the amount 11, 20, 110. So the 5 possible net winning amounts with their corresponding probabilities are given by the probability distribution in table 3. Well, let's check table 3. Where is table 3? Oh, here. Yeah. 110, 20, 11. So this is not winning. So this is not winning anything. The first one, right? Do not get anything back. Or you make it even. So you get $10. Okay, so you make it even. And this you get $11. So because you spent 10, you made $1. This is $20. You spend $10. 20 minus 10, you made $10. And this is the 110. Right? You made $100. So probability is given. The probability for you to get $100 is 0.02, which is 2%. Right, 2%. The probability for you to get $20, right? So the first one is probability for you to get $110 price. $20 price probability is 5%. Probability to get 11, which you win $1, is 40%. Probability you break even is 3%. And probability of losing money is a half chance, 50%. 50%. This has to add up to be 20, so 100%. So 2 plus 5, 7. 7 plus 4, 7 plus 11. So 2 plus 5, 7. 7 plus 4, this is 40. 47. 47 plus 3, so this is 40. 47 plus 3, that's 50. 50% plus 50%, yes. So this value is 1. It has to add up to be 1 to be able to be a probability distribution. Okay, now what do we have to do? Which outcome has the greatest probability? Losing money, right? 50% losing money, losing the $10, 50% chance of losing the $10. Which outcome has the least probability? You see 0.02, right? You only have 2% of chance to make $100. What is the probability that the person will win some money? Will win some money, including this one, and this one. So this 3. So that's how much. Add those probabilities together. That's about 47%. So 3% to make it even. 47% chance to make money, and a 50% chance to lose money. Okay, so this is inclusion-exclusion principle, right? So remember we talked about the cardinal number of the unit E and the F equals the cardinal number of E plus cardinal number of F minus cardinal number of E intersect with F. So this carries on to probability structures. All right, so probability of E unit F equals probability of E plus probability of F, subtract probability of their intersection. Okay, if two events are mutually exclusive, remember the Venn diagram looks like this. Those two subsets are not intersect. But in this case, let's say this is E, this is F. Well, E intersect F is empty, right? It's empty set. They have no common elements. So then the inclusion-exclusion principle formula just reduced to be this, because there's no subtraction, right? Because nothing in the intersection. Nothing in the intersection. So if this is true with the probability, we can conclude the two events are mutually exclusive. So let's see this example. A factory needs 2 raw materials in order to operate. The probability of not having an adequate supply of material A is 5%, 0.05, which means 5%. Whereas the probability of not having an adequate supply of material B is 3%. A study determines the probability of a shortage of both A and B, right? This is a probability of A and B is 0.01, which is just 1%. So earlier we have probability of A is 5%. Probability of B is 3%. And probability of the intersection of A and B is 1%. Let's see the question. What percentage of the time can the factory operates, right? Either operates for A or operates for B. So it means why you change B, E, and F? Oh, so it's called E to be event shortage of A. And the F is to be the event shortage of B. Okay, so probability of E is 0.05, 5%, probability of F, 3%, and intersection is 1%. The question is asking, we can either operate A or operate B, which is a unit. Which is a unit. So probability of E union F equals the probability of E plus probability of F, subtract the probability of their intersection, which is 0.05 plus 0.03 minus 0.1, which is 0.07, or 7%. Use a Venn diagram, right? So this is the use Venn diagram. When we talk about probabilities, sometimes we talk about odds. Odds. What is the odds of something happening? Okay, let's see this. Converting between odds and probability. If the odds in favor of the event E occurring are A to B, then we have probability of E equals A divided by A plus B. Because when we talk about odds, we're talking about, we talk about something, in favor to occur. So if probability of E equals P, we can write this as P over 1 minus P. Just another way of writing it, right? So the odds in favor of E are A to B. Right? So if the odds in favor of the event E occurring are A to B, so just write as A to B, A over B. A to B is A divided by B or A over B. Okay. I don't know why this comes up. So let's see this question. Chance of raining. Suppose that the odds of raining tomorrow are 5 to 3. A ratio is given, 5 to 3. What is the probability that rain will occur tomorrow? The odds for rain tomorrow is 5 to 3, which means the probability of raining, right, let's see this, let's call this A, let's call this B. Remember, probability is A divided by A plus B. In this case, 5 over 5 plus 3, which is 5 over 8. Okay, that's when we talk about odds. Odds are comparing two numbers. It's one number to another number. Okay, let's see this one. How do we find the odds? The probability of obtaining sum of 8 or more when rolling a pair of dice is 15 out of 36, right? Let's see, this is the first die, second die. And we want to add up to be 8. Sum to be 8. So if the first one is 1, we could not get 8, right? If the first one is 2, the second one has to be 6 to make 8. First one is 3, 5, 4, 4, 5, 3, 6, 2, right? The first one can be 2, 3, 4, 5, 6. Then because we have to make up 8, the second one has to be 6, 5, 4, 3, 2. So it's just opposite. Right, just one in this order, one in opposite order. Because those guys, when we add up to be 8. How many? Well, 1 pair, 2 pairs, 3 pairs, 4 pairs, 5 pairs. And A and more, A or more, right? So this is for 8. It could be 9. It could be 10. It could be 11. It could be 12. It's better to make the list of the table. Well, adds up to be 9. We have to start from 3. Right? Then 3, 6, 4, 5, 5, 4, 6, 3. Or to be 10, 5, 5, 6, 4. Only 2. Or to be 11 has to be 5, 6. To be 12 has to be 6, 6. 5, 6, 6, 5. So you will add all those up, it has to be 15. So 15 out of 36. So the question is asking, what are the odds of obtaining a sum of A or more? What are the odds, right? So the probability is 15 out of 36. Okay, so we write it over here. And divided by 1 minus its complement, not happening, right? Not A or more. It's 7 or less. So that's 1 minus 15 divided by 36 is complement. So after calculation, so this is the odd. So the odd of obtaining a sum of A or more for tossing 2 die is 5 to 7. So that's how we calculate odds. Okay, so this paradox you may read on your own. All right, so that's section 2. Let's see section 3, calculating probabilities of events. We're calculating with a theoretical probability or logical probability. Right? We assume every outcome are equally likely to happen. So which means if we have where everyone has one out of, if we have n possible outcomes, where everyone has one, if we, every outcome has 1 out of n. If we, the sample space size is n, so every outcome has 1 out of the size of sample space, which is the probability of a single event. So definition of a probability. Right? So the cardinal number of the event, right? The event means the interested outcomes. So the cardinal number of the event divided by the sample space, cardinal number of sample space, okay, or the size of the sample space. Let's see this example. Now, urn contains 8 white balls and 2 green ones, so totally 10 balls in the urn. A sample of 3 balls is selected. 3 is selected at random, right? So imagine you have 10 in total. You cannot see the color. You know, is the balls are in the urn. You won't be able to see them. You just withdraw 3 of them. So the question is, what is the probability that the sample contains only white ones? Right. So probability of only white, the 3 to be white. So that white. Right. So all white. The first one is white, second one is white, third one is white. Right. Okay. So what is it? How do we calculate the probability? The second question is, what is the probability that the sample contains at least 1 green one? At least 1 green. At least 1 green. At least 1 green. It could be 2 greens, it could be 3 greens. So how do we calculate this? We need to use a combination, idea of combination now. Okay, all 3 are white. So probability of getting wet. Right? How many white ones we have? Right, total I have 10. And the white ones we have 8. Right, we have A white. Do we have A white? Let's check. Yes, we have A white and 2 green. So we have A white and 2 green. A white, 2 green. So the probability of getting all white ones is out of the A white ones comes off 3, right? Because they're white, they wouldn't come from the green ones. We have 2 green ones. But what is the sample space? That's out of 10, choose 3, right? So the denominator is the size of sample space. It's all possible outcomes. But out of 10, so we have A white, we have 2 green, and total we have 10 of them. So out of 10, choose 3. But when we desire 3 of them to be white. And those white ones has come from the white. How many white one we have? We have 8 of them. So that's combination. So out of 8, choose 3. Divided by out of 10, choose 3. So how do we do the calculation? Well, first the permutation, that is A, 7, 6, then divided by 3 factorial. That's out of A, pick 3. Then out of 10, pick 3. That's 10, 9, 8. Then divide by 3 factorial. Or both divided by 3 factorial can be simplified. That becomes 8 times 7 times 6 divided by 10 times 9 times 8. 8 divided by 8 becomes 1. This is 10. Or 6 divided by 3 have 2. 9 divided by 3 is 3. So 2 goes into 10 5 times. So the numerator of 7, denominator will have 5 times 3, which is 15. So the probability of getting all white, 3 of them to be white, is 7 out of 15. Well, now let's see the second one. At least 1 green. At least 1 green, right? So this at least 1 green. So we pick 1 green. The green has to come out from 2 greens. And then we're left with 2 white ones. So this is 1 green, 2 white. Right? This is 2 green, 1 white. So to pick the green ones, we have this many choice. Out of 2 green, choose 1. Out of the white ones, out of 8, choose 2. This many ways, choice 1, choice 2, multiply. Right, so we do the calculation, total we have 64. Right, now we can talk about probability, right? So what is the probability? What is the probability of getting at least 1 green? At least 1 green, which is the cardinal number of 1 green, 64, divided by C, out of 10, choose 3. Well, let's calculate it. That's 10, so this is our sample space size, times A divided by 3 times 2. This is going to become 4, this becomes 3, 120. Right? So 64 divided by 120. We can simplify by 4. Then we have 16. By 4, we have 30. We can keep simplify. Simplify by 4, we have 4 over 15. So it should be 4 over 15. A over 15. Did I do something wrong? I divided by 4. So let's see, this divided by 4. Oh, this they divided by 8. Divided by 8, 120. I divided by 4. If I divide by 4, I get 16. I divide by 4, I get 30. I divided by 4 again. I divide by 2, I get 8. I divided by, oh, it should be 8 over 15. Right? I miscalculated. It's not a 4 over 15. It's a 8 over 15. So it's a 64 out of 120. Let's see this example. A toy manufacturer inspects boxes of toys before shipment. Each box contains 10 toys. The inspection procedure consists of randomly selecting 3 toys from the box. If any are defective, the box is not shipped. Suppose that a given box has two defective toys. So two defective toys. What is the probability that it will be shipped? If any are defective, the box is not shipped. So if two defective toys, what is the probability that it will be shipped? Let's see. The problem is not really new. We solved it, discuss example 1a. The N can be regarded as a box, and the balls as individual toys. The white balls are non-effective toys, and the green ones are defective toys. Remember, we have 10 white ones. We have a white and 2 green. So the random selection of 3 balls from N is just the inspection procedure. And the event all 3 balls selected are white corresponds to the box being shipped, right? Because if any defective is not shipped, so as we calculated previously, the probability of this event is 7 out of 15. There is approximately a 47% chance shipping a box with 2 defective toys. Okay, that's interesting. Okay, let's see this one. Selecting students. A professor is randomly choosing a group of 3 students to do an oral presentation. In a class of 10 students, 2 are on the debate team. What is the chance that the professor chooses at least one of these debaters for the group? So this is 10 students, right? 2 on the debate team. So we have A and 2. So the professor choose 2 to do it. Okay, this is the same as example 1b. Just think of the debate team members as a green balls 2, and the others as white balls 8. Right? The probability of getting at least one debate team is getting at least 1 green ones. In the group is 8 out of 15. Okay, so go back to look for 1b. The calculation is the same. Medical screening. Suppose that a cruise ship returns to United States from England, unknown to anyone. 4 of its 600 passengers have contracted the disease. Suppose that the Public Health Service screens 20 passengers selected at random to see whether the disease is present aboard the ship. What is the probability that the presence of the disease will escape detection? Escape detection, which means no one out of these 20 passengers, no one contracted the disease. So the sample space consists of samples of 20 drawn from among 600 people. Right? Let's see, there's a combination out of 600, choose 20. And there are, right, that combination out of 100, choose 20. The number of samples containing none of the sick passengers is, right, out of 596, 20, because remember 4, right, 4 of them contracted disease. So 600 minus 4, that's 596. So 596 did not contract disease. So that's out of this 596 not contract disease, choose 20. So that means all those 20 people has none of them contracted disease. So therefore, the probability of not detecting the disease is out of 596, choose 20, and divided by out of 600, choose 20. Right? Make sure this makes sense to you. Rolling a die 5 times. A die is rolled 5 times. What is the probability of obtaining exactly 3/4? Okay, 5 times, right? So if we roll 5 times, and each time, remember the sample space, each die, right, we have 1, 2, 3, 4, 5, 6. 6. And we consider we roll 5 times, right? 1, 2, 3, 4, 5 times. And out of these 5 times, we have 4/4. The 4 can happen in any spot. We have 3/4, I mean. We have 3/4. Right? 4 can be here, can be here, can be here, can be only happens 3 times. Right? The 5, 3, so we have 3/4. The other 2 has to be not 4s. Could be anything else. Right? Could be anything else. So that means right here, so out of 5, choose 3. Right? Out of these 5, so because we have 3/4. Out of these 5, 3/4, choose 3 ways. And how many for others? Right? As long as not 4. But it could be 1, could be 2, could be 3, could be 5, could be 6. So each one will have 5 choice. We have 5 choice for non-4. We have another one, not 4, also 5 choice. So we multiply them, right? We have this many ways for 3/4 to happen in the 5 rolling, and the other 2 rollings can be any other number than 4, so which is 5. So multiply them, and for each one, we have 6 possible outcomes, right? So 6 raised by 5. And to do this calculation in the end, we get about 3%, right? So if we roll die 5 times, and the probability to get 3/4, that's about 3%. The complement rule. Remember we talked about earlier using cardinalities, right? Cardinality of the event equals to the cardinality of the sample space with universal set minus the cardinal number of its complement. Those are the elements not in E, but in the sample space. So carry on to probabilities. Right? The probabilities for all sample space, over all sample space, that's 1. So probability of an event equals to 1 minus probability of its complement. Now, let's see an example. Okay, this birthday problem, let's use a simple example first. Then we talk about the birthday problem. Birthday problem is a classic one, but quite annoying. Okay, let me just make an example. Let's see a total die, right? So we know the sample space is 1, 2, 3, 4, 5, 6. And I call my event to be 1, right? To get a 1. Well, what is the probability for me to get a 1? That's 1 out of 6, right? So what is its complement? It's 2, 3, 4, 5, 6. What's the probability of its complement? Well, that's 5 out of 6, right? So indeed, probability of E equals to 1 minus probability of its complement. Probability of its complement. So 1 out of 6 indeed equals 1 minus 5 out of 6. So that's a simple example. Now let's see the birthday problem. We'll end with birthday problem. Okay, so a group of 5 people is to be selected at random. What is the probability that 2 or more of them have the same birthday? Okay. So this is saying for simplicity, just ignore February only have 29 days. All right. And furthermore, assume each of the 365 days in a year is the equally likely birthday. So first, what's the sample space? The sample space is everyone can have birthday in any one of these 365 days, right? So that's the size of sample space, which is 365 divided by 5. Because that birthday could happen in any day of these 365 days in a year. So sample space is really big. Now, this is saying, first select a day, 2 select a different day, 3 select yet a different day, 4 select yet a different day, 5 select yet a different day. What are we doing here? We're trying to find this complement, right? Remember the question is asking 2 or more have the same birthday. So what are we doing here? What are we doing? We are doing here is none has the same birthday. No, none of them have same birthday. So with the first one, his birthday happened in a certain day, and the second one will be another day. Then the third one will be another day other than first and second. So each one has a different day than the previous one. So which means no 2 people have the same birthday. So that's a complement, right? So if we call this E, this is E complement. So no 2 people have the same birthday. None of them have same birthday. So it's easier to find this way, right? It's easier to find this way. It's easier to do probability of E equals to 1 minus probability of complement, which means none of them have same birthday. What is that? That's this. Right? If the first one, his birthday happened a certain day, and second one is different from it. And the 3 is different from the first person, second person. 4 is different from all the previous. The 5th person is all different from the previous. So that's how we find the complement. That's the complement. Okay, so the complement is this. The first one, right, his birth or her birthday can happen in one of these any day in a year, but just fix a day, fix a day. Then the second person birthday has to fall another day. The third person has to fall another day, right? So date is different from the previous ones. And the denominator is 365 raised by 5, right? Anybody. So 5 people, their birthdays can happen in any one of the 365 days. And the complement, probability of the complement is about 97.3%. So out of 5 people, at least 2 people have the same birthday will be 1 minus. None of them have the same birthday, which is 1 minus 0.973, which is about 2.7%. Okay, so this is a very famous birthday problem. Okay, we'll end here. And happy Thanksgiving. All right. See you on December 6th, December 4th, not December 2nd.